Okay, so before we ended the lecture 5, I will give you an examples. Calculations about the grain boundary and dislocation diffusivity. So now we have a polycrystalline copper film with thickness L. So we have a thickness L, and this is a copper, polycrystalline copper film, and this film has a bamboo type grain structures of size D, and the thickness of grain boundary is delta, so it's a bamboo type grain structure. So this is bamboo type grain structure with diameter D, and thickness of the grain boundary is delta. And besides, a bundle of edge dislocation with a core diameter delta and a density rho are in the direction perpendicular to the film surface. So we still have bundles of dislocation, and which is perpendicular to the film surface. So we do have bundles of dislocation, and the diameter is delta, and the density of dislocation is low, and the unit for unit of the density is length of dislocation per unit volume. So it's a length, total length of the dislocation per unit volume. Okay, and the self-diffusivity of the copper ions along crystal grain boundary, dislocation, and free surface are dxl, db, dd for dislocation, ds for free surface. So the first question is, what is the ratio of the atoms diffusing through the dislocation and through the crystal? So what is the ratio of the atoms through diffuse through dislocation and through the crystal? So the ratio, because it's a ratio of the atoms, so we need to know the numbers of diffusing atom in grain through the crystal and also through the dislocation and over dt, right? Then we can divide this two terms, then we will get the ratio of the atoms, right? So based on this, we are going to calculate this first. This is the numbers of copper ion atoms diffuse through the crystal dt. So dn dt is what? dn dt is what? Is similar to the flux times A. The flux of diffusing atom diffused through the crystal is divided as dn, number of diffusing atoms per unit time per area. I just move the A to here. A is the total area, right? So based on this, obey the fixed first law. So we can substitute the minus diffusivity of the grain crystal of a lattice minus diffusivity concentration gradient, right? The same idea can be, we also can get the numbers of diffusing atom diffused through the dislocation dt is also the flux along the dislocation, and A was here, then we move to the right hand side. This is total area of a dislocation, and the flux JD can be expressed like a minus diffusivity of a dislocation concentration gradient. And regarding to A, the area of a dislocation, how can we get this? VDL over V is a volume fraction of dislocation, and also you can convert it. VDL, volume of dislocation, becomes to ADL, is area of dislocation times L thickness, and the volume part, total volume, can be expressed like the total area times the thickness. So you drop the thickness out, then the rest of part is the area of dislocation divided by total area is the area fraction of the dislocation. And this is a volume fraction of dislocation, also can equals to what? The density of dislocation, the unit is length of dislocation per unit volume, so length, so you times the area of the dislocation, then you will get the volume of a dislocation. So now you get this relationship between the ADL, right? Okay, so we can substitute the ADL, the total area of a dislocation, as though A an area of dislocation. This area is the area of one dislocation. So this will be a low A. One area is the area of one dislocation will be what? The area here will be a pi delta over 2 square. So you got this area of a dislocation. So we directly now we successfully get this and this. So the ratio through the dislocation, use this term divided by this term. So we got this results. The ratio can be expressed like this: is proportion to low delta dd and over dxl. So this is the first question. And the second one is, what is the expression of the effective diffusivity in the direction? What direction is perpendicular to the film surface? So effective diffusivity is perpendicular to the film surface, so we don't need to consider the diffusivity contribute from parallel with the film surface. So we ignore the contribution from free surface. So the rest of part we just we need to get the effective diffusivity. We need to calculate the ratio of contribute from the dd and db, because what we have is we have a dxl, dd, and db. So we just need to know the ratios, the volume fraction or the area fraction of the dd in this material, and also dislocation in this material, or the grain boundary in these materials. So based on the previous slide, we know the volume fraction or area fraction of should be the area fraction of the dislocation is equals to this. And regarding to the grain boundary part, if we consider two-dimensional grain boundary, then we know the ratio will be 2 delta over d. And this is a fraction of dislocation, fraction of grain boundary. So the rest of part will be belongs to grain. So we use the 1 to minus this. So this will the ratio of the grain boundary or the grain in these materials. So we can get the results here. And the third one is, what is the minima dislocation density? And that will allow the contribution of diffusing atom along the dislocation is comparable to that along the grain boundary. So the contribution from the dislocation will equals to the contribution from the grain boundary. So this equals to this. So, and then you will get the low. Just move other parameter to the right-hand side, and you input all the parameters, then you get the results here. So the result low will be around 10 to 12 per unit area per centimeter square. Okay. And the last question would be, if the copper film is a single crystal, so single crystal material tell you there's no grain boundary inside these materials, how can you determine the value of dd experimentally? Then we also assume ds much larger than dd, much larger than dxl. So now we don't have grain boundary part. In order to get the dd, so how to do that? So the idea would be similar to what we told you in the region C. There's an example we give you to get the diffusivity of the ground boundary in region C, right? So also, we just deposit a layer of copper isotope on the top of these materials. Then we measure the accumulation rate of this isotope at the backside of the film at different time points. So the idea will be that now the diffusing atoms diffuse through the dislocation. So we need to get the flux. And if we measure the accumulation rate at the backside of this film, so we need to, first of all, we need to get the flux. But the flux, the diffusing atom is through the DD dislocation, right? So we need to times the ratio. Is the ratio of the dislocation in these materials, right? So this is a ratio of the dislocation into these materials, and this is the accumulation rate, right? Numbers of copper, numbers of isotope copper atoms per unit time per unit area. So the diffusivity part can be expressed as minus diffusivity of dislocation concentration gradient. And concentration gradient part, we can use a gradient, so it will be the concentration at x equals to 0 minus concentration at x equals to L. This is a bottom. It's the backside of the film, and divided by thickness of the film. And we also assume the diffusion in the early stage of diffusion. So this term can be dropped out. Then you can get the DD by, as long as you know the thickness, though is the density of a dislocation, thickness of the ground boundary, concentration of the isotope layer deposited on the top of this film, and also measure the accumulation rate. So accumulate of the isotope as a function of time, then you can get the DD. Okay, so I'm going to give you a summary of this lecture. Lecture 5 is crystal defects are fast diffusion channels because atoms at this crystal defects are included in the ground boundary dislocation free surface with higher energy. Okay, and apparent higher energy, that means you have a lower activation energy or energy barrier. So that will allow the atoms, more atoms can overcome the lower energy barrier. So that will result the diffusivity along this crystal defect imperfection side are faster. Apparent diffusivity or effective diffusivity must consider both the diffusivity and also the fraction of the crystal defect in these materials. And different crystal defect means that we have a different diffusion path. And different diffusion path means for different activation energy for each path, okay? So as long as you measure the diffusivity, effective diffusivity at different temperature, and then you plot as a log D versus 1 over T. Then by fitting the slope, like by fitting the curves, then you got several slope, no matter it's 1 or 2, then you can determine the individual activation energy for individual diffusion path. So far we already finished the diffusion in solid materials part, included lecture 1 to lecture 5. And let's give you a quick review for diffusions in solid materials. In the beginning, we'll tell you what is the kinetics. It is actually focused on the steady state flow and also is an irreversible process. By calculate the entropy production rate, then we can know how fast this kinetics process is. And also, as for diffusion in materials, the first criteria, first thing you need to deal with, you need to find how many possible driving forces apply on the system to drive this mass transport, right? So and you how many you need to find them out. And next in lecture 3, actually we give you how to formulate the diffusion equation and calculate and get the corresponding solutions in macro scale, right? And also, okay, then in lecture 4, actually we teach you how the atoms diffused through crystal materials is in micro scale. And we also show you several different types of atomic diffusion mechanism. So not only in metals and also in ionic solids. And this is this lecture 4 we focus on single crystals, and lecture 5 we introduce crystal imperfection size to you and help you to deal with the materials with polycrystalline structures. So we show you how to deal with polycrystalline materials, and also show you different diffusion mechanisms in grand boundary diffusions, and also give you some examples about the dislocation and surface diffusion phenomena involved in your materials. So now we are going to move to the second part in this kinetics class. Is we are going to spend 2 lectures 6 and 7 to talk about the chemical reactions, which included the homogeneous chemical reaction and heterogeneous chemical reactions. And the difference between homogeneous and heterogeneous is based on how many phases of reactants or products involved in these chemical reactions. If it only happens in one phases, then that will be the homogeneous chemical reaction. If the phase is equal or larger than 2, then we will call that as heterogeneous chemical reactions. Okay, so let's move to lecture 6. Lecture 4, homogeneous chemical reaction part, you can simply separate into 2 sections. The first section, I will give you an overview of chemical reactions, how to classify the chemical reactions, and also will help you what's the rate equation. For example, like for your interesting chemical reaction or chemical equations expressed like this: hydrogen react with oxygen, then you will get the water. And based on this, yes, you have a chemical equation, but how to get the rate equation? Can we directly formulate the rate equation based on the chemical equation we have? Not exactly, right? It's related, but not exactly. The rate equation involves 2 parts. The first part is we call the rate constant. Rate constant is correlated with temperature and also the energy barrier between the reactants and the products. And the second portion will be related to the concentration of reactants, and the order sometimes will be identical with the coefficient we have here, A and B, and sometimes are not the same with A and B. So that can be easily divided elementary and non-elementary chemical reaction. And for the second part, we are going to show you how to measure or get the reaction order. This is the reaction order from experiments for your interesting chemical equations or your new developed chemical equations by experiments. So we will teach you some method to get the reaction order for rate equation. So let's move to the first part is overall of the chemical reactions. So the definition for chemical reaction is the formation of the products as a result of interaction between reactants through collision of reactant molecule or self-transformation, which is a decomposition of the reactants. So this kind of reaction, we call it as a chemical reaction. If you plot the figure through as a function of free energy, by using the free energy as a function of reaction coordinate, then now we have a reactant A and B, product C and D. Then the total free energy of reactant A and B will be like this. And this, as long as these reactants have sufficient energy to overcome this energy barrier or activation energy, then this reaction, you will get the product C and D. And the energy, the difference of the free energy between the product and the reactants, we call the delta G. It's the Gibbs free energy. So based on thermodynamics, we know the systems always moves to the lowest free energy of the system, to lower the free energy of the system. So we can predict whether this chemical reaction will happen or not based on the delta G is negative or not. And also, so this will serve as a driving force to these chemical reactions. And yes, now you know this is driving force. So based on the lecture 1, we know the atomic flux is equals to mobility concentration and driving force. So the driving force here is minus Gibbs free energy gradient, right? Okay, so next, what is the spontaneous chemical reactions? Spontaneous reaction tell you that this chemical reaction happens on what? When this is spontaneous, so you don't need to apply extra driving force to drive this reaction. So A and B will, as long as A react with B, they will become C and D directly. So for example, that the salt dissolve in water, ice melting, and irons roasting. Yes, although it is spontaneous chemical reaction, but the external driving force, the Gibbs free energy definitely is negative. So Gibbs free energy can serve a driving force for this system, for these chemical reactions. So the reactant happens as a result of reduce of total free energy of a system and also increase the system entropy. And the reaction kinetics depending on what? Depending on the concentration of reactants and also the fraction of energetic reactants. So what's the fraction of energetic reactants? That means how many reactants have sufficient energy to overcome the energy barrier. So when you try to write down the rate equation for these chemical reactions, can be equals to rate constant, concentration dependence, concentration of the reactants. And this rate constant included what? Included this portion exponential minus activation energy over kT. This portion is the fraction of energetic reactants, right? This based on the Maxwell Boltzmann distribution, we know the fraction of the reactants which have a higher energy, higher than activation energy, is proportion to exponential minus delta EACT divided by KT. Okay, and rate equation also will proportion to the concentration of reactants, and the order here is A and B. in this case definitely implying that this is elementary reactions. That means really A moles of A react with B moles of B during the reaction. So this we call elementary reaction. We will talk this definition in following slide. Okay, so this is a Maxwell-Boltzmann equation. As we mentioned, that we can know the probability of the fraction of the reactants have sufficient energy to higher than activation energy. Okay, so regarding yes, you have the chemical equation, but we want to know the performance of this chemical equation. So what parameters will affect the performance of this chemical equations? So we use the reactors, input and output as an example. Yes, we input the reactants inside the reactor, then we will get the output. Then the output can consider the performance of this chemical reaction. So the reactants is going to react each other inside the reactors. So the contacting pattern will affect the performance of the equation, right? And also the kinetics. What's the contacting pattern is how the atoms contact, how the reactants contact each other. So you can, by designing different types of reactors, you can change the contacting patterns of the reactors. And kinetics is what we are interested in is the chemical reaction. What kind of chemical reaction you choose? So that will affect the rate constant, the energy barrier, activation energy, right? So the kinetics, what kind of chemical reaction you choose for these equations. So the performance of these chemical equations means that the output of these chemical reactions. So will depends on what types or what kinds of reactants you choose. What's the rate equation for this specific chemical equation, and what's the contacting patterns between the reactants. So here we introduce you 3 different types of contacting patterns of reactors. So as we mentioned, contacting pattern is how reactants are mixed and react with each other. So here, the first one is we call a bench type. The bench type, that means you put the reactant into the beaker and you will put the stirring bar at the bottom. So during the reactions, you can expect the concentration at anywhere inside the beaker are uniform. But the concentrations does change with time. So does change with time. Because the reactants will react, then the concentration of reactant will decrease, but in the meantime, the concentration of product will increase. So the concentration does change with time. And the second one, we call it is a Plaque Flow. What's the Plaque Flow? We put the reactants here, and this reactants will flow and react each other, right? So when you check the concentration at different locations, then you will find the concentration does change with locations and also with time, right? Because the reactants flow and pass through this tube-like reactors. So no matter it's a concentration at different locations, or the concentration at one location, but it also changes with time, right? So this and the third one is the mixed flow process. Means that we ended the reactant here, and also into the beaker, and we use the stirring bar here, and we still have an outlet here. So the difference between this one and the bench type is we always refill the reactants to allow the concentration of reactants keep constant, and we definitely will constantly generate the product, so we have an outlet for the product. So in this case, the concentration of reactants at anywhere inside the beaker will be constant, the same with the bench type. But the different part is because we always refill the reactants, so the concentration does not change with time. The CT equals to constant. Okay, so it is a uniformly mixed, same composition everywhere within the reactor and also at the exit. So because here is the kinetics care about the concentration, how the concentration change with time, and hope the system will be the uniform of concentration will be uniform at anywhere. So the chemical reaction we talk about in kinetics belongs to bench type. Will be the bench type because in this kind of contacting patterns, the concentration inside the beaker are uniform, and also the concentration change with time. So what we are interested in. We want to know how the concentration changes with time. So we use a bench type in here. Okay. So how to classify the chemical reactions? Usually we by how many phases involved in these reactions. So if the reaction only involved in one phase, that will call a homogeneous chemical reaction. If it involves two or more phases, we call it a heterogeneous chemical reactions. And some people will ended the catalyst inside this chemical reaction. So some people will classify as non-catalyst 1 and catalyst 1. And for the purpose to end the catalyst is to reduce the energy barrier or activation energy to speed up the reaction rate of the chemical reaction. And some people probably will ask, what's the difference between the homogeneous and heterogeneous in reaction rate? For the homogeneous one, because the reactants are in the same phase, so we don't need to consider the transport of the reactants. But for the heterogeneous one, because for example, like the reactants belongs to gas and solid, liquid solid, and gas liquid, then we need to think about how fast the gas can be transported to the surface of a solid. So we need to consider the transport part, and also we need to consider the transport of a liquid molecule to the surface of a solid. So transport, that means it's definitely spend some time, right? So we need to calculate how much time of this transport between the reactants in different phases. So this is a very important part here. Okay, so today we just ended here.